In the last video, we talked about what an ant colony does to the physical structure of your soil, the tunnels, the water infiltration, the nutrients. If you have not seen that one, go back and watch it, because everything in this video builds directly on top of it. But today we are going somewhere stranger. Somewhere most gardeners have never thought to look. Because the ant colony in your garden is not just an engineering project, it is a society, a functioning civilization with division of labor, chemical communication networks, collective decision-making, and a level of internal organization that has made it one of the most studied systems in all of biology. Not because it lives in soil, but because what it does without a brain, without a leader, and without anyone in charge, scientists still cannot fully explain. Let's start with the number that changes how most people think about an ant colony entirely. A single mature colony of certain common garden ant species can contain anywhere from several thousand to over 100,000 individuals, all of them descended from one or a small number of queens, all of them working from the same genetic blueprint, all of them coordinating their behavior without any central command structure issuing instructions. There is no ant in charge. The queen does not direct the colony. She lays eggs. That is essentially her entire functional role. Everything else, the foraging routes, the defense responses, the nest expansion, the temperature regulation, the food storage, all of it emerges from thousands of individual ants, each following simple local rules and somehow producing complex, adaptive, intelligent behavior at the level of the whole colony. Biologists call this emergent intelligence, and the ant colony is one of the best studied examples of it on Earth. Your garden contains, underground, right now, one of the most sophisticated examples of distributed problem solving that exists in the natural world. And it has been running continuously, probably for years, without you ever knowing it was there. Here is how that coordination actually works, because it is more elegant than almost anyone realizes. Ants communicate primarily through pheromones, chemical signals deposited as they move. When a foraging ant finds a food source, it returns to the nest, leaving a pheromone trail behind it. Other ants encounter this trail, follow it to the food, and on their return journey, reinforce the trail with their own pheromones. The strength of a pheromone trail is proportional to how recently and how frequently it has been used, and trails that are not reinforced evaporate within minutes. This is simple mechanism. Lay a trail, reinforce successful trails, let unused trails fade, produces something remarkable. The colony collectively identifies the shortest and most efficient route to a food source, not because any individual ant calculated it, but because the mathematics of reinforcement and decay naturally converge on the optimal path. This phenomenon is so robust and so mathematically elegant that computer scientists have built entire algorithms around it. Ant colony optimization is now used in logistics companies to plan delivery routes, in telecommunications networks to route data efficiently, and in manufacturing to optimize production scheduling. The routing software that some shipping companies use to plan truck routes is, at its mathematical core, based on how ants find food in soil. The colony under your garden bed is running the same algorithm that some of the largest logistics networks on the planet eventually adopted, millions of years before anyone built a computer. Now let's talk about something almost nobody knows about ant colonies in soil, and it involves temperature. Many ant species are remarkably precise about the internal temperature of their nest, and they achieve this precision through architecture rather than biology. The chambers of a nest are positioned at different depths, specifically because temperature varies with depth in soil, staying cooler near the surface and more stable deeper down. Worker ants brood the eggs, larvae, and pupae between chambers throughout the day, relocating them to whichever depth currently has the temperature closest to optimal for development. On a hot afternoon, brood gets moved deeper. In the cool of early morning, it may get moved closer to the surface where the sun has begun warming the upper soil layers. This is not a passive response. It is active, continuous, colony-wide climate management executed by thousands of workers responding to temperature gradients they sense directly through their bodies, with no instrumentation and no central coordination, maintaining brood chambers within a narrow temperature range that maximizes development speed and survival. The ants in your soil are running a climate control system more responsive than most home thermostats, recalibrating constantly, every day, for as long as the colony exists. There is also a defensive dimension to ant colonies that connects directly back to soil health in a way most people never consider. Many ant species are aggressively territorial against other ant colonies and against a wide range of soil-dwelling pests. Larvae. A study examining ant activity in agricultural soils found that areas with established ant colonies had significantly lower populations of certain root-feeding grub species compared to areas without ant activity, because the ants actively prey on or displace these larvae during their normal foraging and excavation behavior. The same colony that is aerating your soil and fertilizing it with nitrogen is also patrolling it, and that patrol has consequences for which other insects can successfully establish themselves in that soil. An active ant colony does not just build your soil. It defends the territory it built, and some of what it is defending against are organisms that would otherwise be feeding on your plant roots. Here is a fact that tends to genuinely surprise people. Ant colonies can be extraordinarily long-lived, far longer than most people assume for an insect. While individual worker ants typically live anywhere from several months to a couple of years, depending on species, queens of many common species can live for over a decade. And because the colony persists as long as the queen does and new workers are continuously produced, an established ant colony in a stable patch of garden soil can function as essentially the same biological entity, the same society for 15, 20, in some documented cases even longer years. The nest entrance you see in your garden bed this spring may be the same colony, the same continuous society that was there 5 years ago, 10 years ago, quietly building soil structure, cycling nutrients, and defending its territory the entire time, completely undisturbed, completely unnoticed, doing exactly the work we talked about in the last video, year after year, without interruption. When you destroy a nest like this, you are not just destroying a structure. You are ending a society that may have been continuously operating in that exact spot for longer than you have lived in that house. This brings us to something practical, and it is the piece of information that most changes how people respond when they find an ant nest they were not expecting. Not every ant species you find in your soil is the same, and the differences matter enormously for how you should respond. Some species are almost entirely beneficial with no meaningful downside in a garden context. Others can become genuinely problematic, particularly certain invasive species that displace native ant populations, disrupt the seed dispersal relationships those native species evolved with local plants, and in some cases damage structures or electrical equipment, which is a real issue with a small number of specific species. The point is not that every ant nest deserves the same response. The point is that the default response, destroy on site, treats a beneficial 15-year-old soil-building society and a genuinely problematic, invasive colony identically, which means you are very likely destroying far more of the former than the latter, simply because almost nobody pauses long enough to tell the difference. A few minutes of observation, watching what the ants are carrying, what they seem to be doing, whether they are displaying the kind of aggressive behavior associated with specific problem species, tells you more than reflexively reaching for poison ever will. What we are really talking about across both of these videos is a shift in how you see the ground in your own backyard. Underneath the surface of an ordinary garden bed is a distributed intelligence system that solves logistics problems better than some software companies. A climate control network that maintains stable temperatures for thousands of individuals without instruments. A defensive force that influences which other insects can establish in your soil. And potentially a continuous society that has been quietly running for longer than you have lived in your home. None of this required your help. None of it required your awareness. It has been happening regardless, in the dark, under your feet, this entire time. The next time you see that small mound of fresh soil at the edge of a garden bed, you now know more about what is underneath it than almost anyone who will ever walk past it. A pheromone-based routing network older and more elegant than modern logistics software. A climate-controlled nursery moving with the sun. A defensive perimeter. Possibly a decade or more of uninterrupted continuity. All of it right there, doing exactly what it has always done, waiting only for you to leave it alone. What is the most surprising thing you learned about ants from either of these two videos? Tell me in the comments below. I read everyone. And I love seeing which facts actually land and change how people think. And if you have not seen part 1 yet, go watch it now, because between the 2 videos you now have the complete picture of what is happening beneath your garden every single day.